To není test. Je slyšet? Zkouška.
And it's time for the next talk, so please take your seats and welcome Petr Chalupa.
Hello everyone, thank you for coming. My name is Petr Chalupa. I work for Oracle Labs, which is a research group within Oracle, and I'm part of a team working on a new fast implementation of Ruby language called JRuby plus Truffle. Before I start, I would like to make sure that you understand that projects I'll be talking about are research projects, they are not Oracle products, and any opinions are mine own. Before we start talking about the multilingual VM, I'll describe how it usually goes when you are implementing a new programming language. So at first stage, you have some nice ideas about a new language, so you want to try them out. So you write a parser and abstract syntax tree interpreter for it. Usually it's some high-level language, so you are able to prototype it very quickly. And when you are happy with it, usually rewrite the parser and the abstract syntax tree interpreter in some compiled language, so the language is faster. So usually in C, C++, or maybe Java. And you let the world know about your language. So then people love your language. They started to use it, but they complain that your language is slow. So you can go and add a byte-code interpreter to improve the performance. So your language is faster, but it's still not fast enough. It's still like 30 times slower than Java, or something like that. So to get even better performance, usually improve the bytecode interpreter by doing some hand optimizations in assembler, and you also have to add just-in-time compiler. It's still not fast enough, because what you really need is very well optimizing just-in-time compiler, with all the optimizations which usually are in mature compilers like for Java, GCC, V8, and similar languages. And if your language is dynamic, which is most of them today, you also need to be able to do speculative optimizations, to be able to assume things like that my methods in my language are the same, that they were not redefined, or that constants in my language are still constant, that you didn't change them, and stuff like that. And if you have speculative optimizations, you also have to implement the optimization. So you are able to go from your compiled code, which is based on some of the assumptions, back to the interpreter, and in the interpreter handling the new constant or re-implemented method and stuff like that. So the problem with this approach is that it's really time-consuming. It's an enormous and difficult effort, and I didn't even talk about garbage collectors, which is a similarly difficult thing to do. So this usually could take decades until you do all of these steps and you get the performance to the performance level of Java or something like that. But there is another option. You start by prototyping your language with the parser and abstract syntax tree interpreter, but you will use a Truffle framework and a Graal compiler, which is the main technologies I'll be talking today about. And you will let the world know, and it's already fast. Because this framework and the Graal compiler takes care of all the optimizations you would otherwise have to do. And before I go to show some of how Graal and Truffle works, I'll show you a few numbers. Maybe to convince you a little that this is not just a research project, but that there are real implementations of languages which are already competitive. So for example, there is a JavaScript implementation which already competes with V8 engine and SpanderMonkey. The Graal compiler, of course, can run instead of the C2 server compiler, so there's the same performance as the server compiler for Java, and it's even better for Scala because Scala has lots of dynamic features where server compiler was not really designed for that. And another example is Ruby implementation, where there is nowadays no other really fast Ruby implementation. So there are also other languages in this graph to compare. So the first one is implementation of these benchmark in Java. The second one is JRuby plus Truffle. So it's just a little bit behind. It's a little bit faster than Node.js. And this is another alternative implementation of Ruby. It's about 20 times slower, and the referential implementation MRI is about 50 times slower than Java implementation. Sorry, than the JRuby plus Truffle. So this system really can create or support implementations of dynamic languages very fast. So now let's talk a little bit about how it's done. So the first piece of the puzzle is Graal compiler, which is a high-performance optimizing just-in-time compiler for Java HotSpot VM. What that means is that you can use it as the JVM has two compilers, client compiler, server compiler, and the Graal compiler can be used instead of the server one, so you get the same performance. But the main difference is that this compiler is written in Java, and it uses annotation and annotation processors heavily, so it's much easier to add new optimizations into this compiler than to the one which is written in C++. And another key part of it is that since it's written in Java, so it's just a library, and you can use it as a library, configure how you want your methods to be compiled. So for example, if you want them to be compiled with speculative optimizations or without, and you can tell it what you want to compile, which is very important for the second piece, the Truffle framework. It's designed for the speculative optimizations, and of course it supports the optimization, designed for exact garbage collection, and it has aggressive high-level optimizations, partial evaluation, and partial escape evaluation. The partial evaluation is really important for the Truffle framework. I mention it again on the next slide. And it's open source. The second part is the Truffle framework, which is a language implementation framework, which uses the Graal compiler. And basically, it's a self-optimizing abstract syntax interpreter, which means that when you implement your language in this framework, so you create the AST nodes for your language, and these nodes can replace themselves with specialized versions based on the program which is executed. So for example, if you have somewhere addition, and your language has dynamic typing, so you can specialize to adding just 2 integers, which translates to just one instruction. It uses custom method inlining, which is important when you have an abstract syntax tree of your language described in the Truffle framework. And when this method becomes hot, you ask Graal for a compilation of this tree of your method, which is implemented by all execute methods on those nodes. So we have a custom method inlining, which basically inlines everything. So if you give Graal, for example, 200 nodes, which is representing some high-level methods in your language, Graal, first thing it does, it inlines all of those Java methods implementing your method together and creating one big compilation unit. And then it applies partial evaluation, so it evaluates away all the constant parts which are coming from the nodes implementation, and only the most basic parts will remain. There is also support for the assumptions I've mentioned before, to assume that the constant is still constant, that you have constant number of fields in your classes and stuff like that. And it's open source. So now let's talk a little bit about how the Truffle framework specializes based on the types it sees. So at the beginning, we have a method which is represented by these 5 nodes, and they are in an initialized state because they didn't execute any code yet, so they don't know which types will flow through this method. Then if you start to execute, sorry, just backing a minute, all nodes start in an initialized state, and then they transition to a different state based on the types they see. So to string, double, or integer, and the end in generic. And it's it's an oriented graph. You cannot go back from double to integer because then you could have an implementation of the method where it would be switching forth and back between 2 different types, which is not what you want to. You need the nodes to stabilize so you can compile them. So if this particular method sees 2 integers and one, for example, some generic object at the end, the nodes will specialize to 3 integers and 2 generic nodes. And after this method becomes hot, it's fed to Graal and compiled together in a single compilation unit. But later, if one of the integers will see a double, then you have to go back from the compiled code because the compiled code doesn't know how to handle doubles. So you go back to interpreter, and the node knows how the node at the bottom knows how to handle doubles. So it can replace itself with another node which is handling integers and doubles. So the AST abstract syntax tree can respecialize, and after it becomes hot, it can compile again. So let's look at a little bit more concrete example, how it optimizes some mathematical calculations. So this one is to calculate the volume of a sphere. The example is in Ruby. So it just floats. This is a constant of p, and the last operator is the power of 3. So a dynamic language, to calculate this simple formula, usually has to do all of the steps on the right side. So the red ones is the actual calculation of values, or if it's execute free, it's just retrieving the constant. And the black ones are representing checks which are necessary to perform in dynamic language to be sure that, okay, that some particular variable is still float, that it didn't change to string and stuff like that. And the other group of checks is checking that the p constant was not redefined by some malicious code, or that the multiplication method is still the same. Because in dynamic languages, you can often redefine the method, so you have to check that somebody didn't do that. So at the beginning, you have abstract text tree initialized again, and as you go and execute, the node will profile based on the types it sees. So the blue one is the only one integer, the red ones are doubles or floats, and there is one generic format. And as the nodes replace themselves, they also know that their children are also specialized to doubles in this example. So, for example, the division in this tree will not call some generic execute method which is returning Java object. It will call execute double. So when you compile this, you see that all of these nodes are just working with primitive types. So all of these checks for that everything is float go away. So you can reduce the steps to this. And they are just, what remains are the checks that the float class is the same, pi constant is the same, and stuff like that. So to remove it, we need the global assumptions, where assumption is basically just some flag which you can have in your runtime, in your implementation of your language, that represents that constants is the same, class does not have any new methods, and stuff like that. And when you initialize assumption, it's in a valid state, so the flag is true, and you can invalidate it once. So in an interpreter, it's just a Boolean check, if it's true or false. Based on that, it goes through different branches. But when an assumption is compiled, it always assumes that it's true, which means that it goes away completely in your compiled code. There is no overhead for having assumptions in your code in the compiled path. And the way how it's done is when you are compiling code which contains assumptions, it goes away because it's assumed that it's true. But also after it's compiled, it's linked with the instance of the assumption. So when somebody goes and redefines a constant, you then can invalidate the assumption which was representing that this constant is stable. And the assumption will invalidate all of the code which was depending on it, all of the compiled code which was depending on it. If there is any threat in that code, it will de-optimize and continue in the interpreter, where it can handle constant redefinition. So we can then define a few assumptions for example, the power method, that is still the same, for math, p constant, and stuff like that. And if we do, it removes all the other checks. So in the compiled code, only the calculation will remain. But of course, because at the bottom there are just constants, so it will be partially evaluated, shortened even further. So we've started with this, and that's the result. This doesn't work just for some mathematical computations. It also works on higher level examples. So these are again in Ruby. So for example, if you have 3 numbers and you want to get the middle one, you usually write something like this. So you will create an array of the 3 values. You will sort them, and you read the middle one, which in most of the implementation leads to allocating an array, then probably calling a quicksort on it, and getting out the value. But in Ruby plus Truffle, if we see that the array is small enough, we can replace the quicksort algorithm with something simpler. So compiler can see through it and partially evaluate it based on the fact that the array has a constant length. So it will reduce to just these two comparisons. So there will be no array allocation or stuff like that. Then, for example, if you have a constant hash, you apply a map function, then you will be retrieving just values and reading the first value. It will also evaluate to just one. And this also works for some dynamic programming, like if you have a -2 and you, via reflection, you retrieve the object which is representing the method for absolute value. And if you dynamically call it, it also evaluates to just 2 during compilation. Or for dynamic call of a multiplication method, again works the same. And it also works for much more complicated examples. So if you have a class bar and you are creating new instance and calling a method foo with 3 arguments, but the class itself doesn't have a method foo. So it calls a callback, which is handling when a method is missing. So it's called with the method name and the remaining arguments. And this particular implementation checks if foo has a method foo. If it does, it calls it. It's again a dynamic call. And the implementation of the method is just creates a hash from the arguments, maps them the values from the hash to an array, reads the first element, finds the middle one, and adds them together. But all of this can be compiled to just a constant during compilation. But the system is not good just for implementing one language. It's also good for language interoperability. Because if all of the languages on this system are using Truffle framework, then all of the AST nodes from those different languages are sharing the common parent. It's just a Truffle node. So you can do language interoperability quite easily. And because they are the same nodes, you can also inline across languages. So for example, if you have a method in JavaScript and you export it so it can be imported in a Ruby language, then you can call from some Ruby method this JavaScript method, and when this gets hot, it can inline the body of the JavaScript method and it's compiled together. So the language boundary is eliminated completely. I had a prepared demo about this, but I have to apologize because I am doing the presentation from a different computer. We were not able to hook it in, so I tried at the end maybe to show it with some bad colors, but we will have to get to it later. And there is also another project called Throng, which is Truffle interpreter for LLVM intermediate representations, which means that you will be able to run C and C++ on top of this system. And this is very useful for languages like Ruby or Python, where Ruby and Python are both written in C, and where they are not fast enough, people usually write C extensions. So if there is a different alternative implementation of the language, it has a really hard time to be compatible with this referential implementation, because it usually doesn't have the same C API, or it doesn't use C at all. But on this system, you can just execute the C extensions with your language, and it will work. And as a bonus, it will be even faster, because it can inline the C functions to your normal Ruby or Python code. And last project I would like to mention is called Substrate VM, because another problem which is usual when you have alternative implementation, for example, if you have a Ruby which is written in C, and that starts immediately. And there is alternative implementation JRuby, which is based on JVM, so it takes some time to boot up the JVM. And this system, of course, works on JVM, so it takes like a second or two. So this is not really good for development. In some languages, you have lots of small command line utilities in the language to help you with the development. So if you would have to wait for each one of them to boot up for 2 seconds, it would be really not good. So to solve this problem, there is a Substrate VM project, which basically takes your interpreter implemented in the Truffle framework and compiles it ahead of time. Again, using Graal compiler with just some different configuration. You turn off the dynamic speculations, dynamic speculative optimizations, because you cannot recompile it again. So it will do just the normal optimizations. And when you have that, it will start immediately as the normal C implementation. The one limitation currently is that since this is designed just to run Truffle languages, so it doesn't have a usual Java, unless there is Java implemented of Truffle. And but of course, it can do all of the optimizations which are available on full Graal VM. So just to summarize, on top of, there are different language implementations, like Sulong is missing there, and JavaScript, R, Ruby, Python, and they are all using Truffle framework that can run on top of Graal VM or Substrate VM. And I would like also mention that we are looking for new people to help us with working with the JRuby plus Truffle implementation, or maybe other projects. So if you're interested, come talk to me. And that's it from me. Thank you for your attention. And if you have any questions, I'll be happy to answer them. Maybe after that, I'll try to show you the demo, but I'm not sure how it goes.
So one thing I wonder about Graal VM, it looks like looks like a fairly standard optimizing compiler compared to C1 or C2 written in Java. Does that thing that it's written in Java enable some essentially new optimizations, or is it just that it's easier to write the optimizations in Graal than in C2?
I think it's mostly about that it's easier to write them. This the way how it's structured. Then usually how it goes is that you have some really abstract definition of the node for the intermediate representation in the compiler, and use lots of annotations to describe that it has these relationships with other nodes, and annotations processor will generate all the boilerplate for you. So it's much easier to do. It's not like that it would enable something new. Not that I know. Thank you.
So I have a question about the process. Is there any plan to improve that in the future, or give some hints, like before the first run of the application, so that it doesn't have to take because, for example, the compilation or optimization of something to 22, it first needs to run the code to be able to optimize that. So if there was some process as part of compilation, even for interpreted language, so that I could package this information so that the customer, the user, the end user would start with some optimization or hints that could be used. Is this planned for doing? Thanks.
So currently we are not working on that because it would improve just like few first seconds when the code is interpreted. And it goes quite fast through the compilations and to the compile core code, when it's quite fast. So right now this is not a priority. It would be possible to make some static analysis ahead, to, for example, pre-specialize some nodes, but this is really also not an easy task to do for dynamic languages, to do this correctly. So, and the gain is just for first few seconds. So
I can imagine that this could be part of the CI or running the standard tests. we run it anyway, but I don't know how big problem is it in production. Thanks.
No more questions? Are you all waiting for the demo?
Okay, let's see how it goes. Could you switch my computer? Okay. Sorry, I forgot to plug it in. Okay. So now you know why I've used a different computer because of the colors. So I have here a console which allows me to run pieces of code in different languages. So I'll start by switching to JavaScript, and I will define a function for subtraction, and I will export it under the subtract symbol. And then I can switch to Ruby language, where I import the exported function, and I store it in a constant. And now I will define some Ruby function which will be using this exported JavaScript function. Oh, sorry. Okay. So the first one is in JavaScript, exporting the subtract function, and the second one is just storing in a constant. Or maybe I do this. Okay, it's not better, but okay. So now I define some function which will be using it. So it calls the JavaScript function here. And I also enabled some debug output for how the functions are inlined into each other. So now when I run the test function 100,000 times, it will trigger the compilation. And we can look up in the, it's not really, okay, in the output how it was inlined. So the first one is, right, this times is the, okay, I will do. This is the same example I've used for how did I run the functions. So this times method is this first one. Then it inlines the test method implementation, which is this one, and continues inlines times inside the test method again. Then it inlines the inject method. You can see here, it inlines its method and continues to inline the JavaScript interoperability root node, and it also inlines the body of the JavaScript function on this line. So if we then go to a graph, which is just a representation of the intermediate representation in Graal of the methods, of the method we are compiling. So in this example, it's the top level times method, which contains inlined all of the test method, again times, inject, and at the end, the JavaScript method. So we can look up that at the bottom there is the integer subtraction there. So it's part of one compilation unit, which is then optimized by Graal. This is at the beginning before all the compilations are applied. Yeah, so that's it. It was short. Any more questions, maybe? Okay, thank you for your attention.
Takže nepoužívať Mac. Takže jsou ty časy, kdy člověk měl jistotu, kdy byl problém s Linuxem a Macy fungoval.
Já jsem v životě s tím neměl problém. Tak tady, já si myslím, že to je nějaký sabotérství tady.
Se tam jako korunka.
Ze strany univerzity.
Jedna, dva.